Hello and welcome back to CEN 202 Mechanics of Materials. In this unit, we're going to be talking about columns. Columns are long, thin members that support compressive loads, as shown here on the left. These are relatively complicated to design because the primary mode of failure is buckling. As a result, you need to take into consideration a number of different aspects of the columns, things like length, material, supports at the ends, etc. So there's a number of different techniques we're going to look at. These are covered in your Hibbeler text, Chapter 13, and I recommend you review it prior to looking at this presentation. Up until now, everything we've looked at has been in stable equilibrium, meaning small changes in force are not going to have a dramatic change in the performance of the material. Unfortunately, with columns, the dominant mode of failure is actually buckling. This is very different from tension, compression, and shear. What we find is as we load our column, eventually the load is going to get to the point where it's going to cause the column to bend, at least a small amount. That bending is going to give us a small level of lateral deflection, meaning the beam, in this case the column, is going to be no longer straight. When that starts to happen, it turns out that the stresses are going to increase, and they're going to increase not only due to the axial load, but they're also going to be affected by that deflection. As long as that deflection remains small, the column will remain stable. But if it exceeds that level, we'll find that it's no longer going to be in equilibrium. Eventually, continued small increases in the load will get us closer and closer to what we call the critical load. And if at that point we exceed that critical load, there's a high potential for a very large sudden deflection, which can result in the beam buckling and the overall collapse of the structure without warning. Now, it's important to understand that this collapse is not due to the failure of the actual column material. Yes, we have exceeded the yield strength of the material in a small portion of it, but the actual load and the actual failure is due to the column and the structural failure of that. And it's when the column moves from being in a stable configuration to an unstable configuration. To understand the difference between stable and unstable equilibrium, let's take a look at this hinged bar shown below. If you take a look at the configuration on the left, labeled as stable equilibrium, you'll see that the force is a tensile force that is going to be pulling on the structure. On the right, however, labeled as unstable equilibrium, we now have a compressive force. Looks very similar to the columns that we've been discussing so far. The reason why configuration A is considered stable is the load is such that if we make small changes, in this case small changes in rotation, since it's a hinge bar, the moment that's going to be created is actually going to tend to restore the bar back to its initial condition. As a result, small changes have very little effect on this overall structure, and it's somewhat self-correcting. On the other hand, if we look at configuration B is considered unstable equilibrium because in its initial position, the overall structure is in equilibrium. The fact is this downward force is being counteracted and it will remain stable if nothing changes. But keep in mind, it has to remain perfectly vertical. Any small changes to the left or right is going to cause a small rotation, which is actually going to magnify the effect and actually cause a greater rotation. As a result, there's no self-correction here at all. If anything, the instability is going to reinforce itself. So to summarize, if we consider a system in equilibrium, we find that anytime we make small changes in things like displacement, rotations, they're generally going to affect the overall position of the structure, and it's going to produce some resulting force. If it turns out that the forces essentially correct the system, moving it back to the equilibrium position, then that system is stable. And for most of the structures that we have looked at, that generally is the case. On the other hand, if the forces do not do this, if the forces instead increase the displacement, then the system is unstable. And that's what we're going to find to be the case with columns. Now let's consider an ideal column. If you take a look here, you'll see one shown on the right. It is pinned at the top and bottom. Pin supports allows the column ends to rotate, but it prevents them from moving left to right. This is shown vertically, but keep in mind, columns don't necessarily have to be vertical, although they commonly are, as they tend to support the weights of structures and other elements. But any long, thin member under a compressive load is treated as a column. In terms of our analysis, we're generally looking for the strength of the column, and that's defined by the smallest load that's actually going to cause it to fail. This is referred to as the critical load or the Euler load. This is named after Leonhard Euler. He's an 18th century Swiss mathematician, scientist, and engineer. He's also considered one of the greatest mathematicians of all time. Made a number of different contributions to science, engineering. Done a great deal with material science and with fluids. In fact, he's the one that came up, or at least defined, the logarithmic base E. It's considered the Euler number. So if you have not seen him, the name used before, you probably will in your study of engineering. Turns out that for any load below that, we really don't have to worry about it. The column acts essentially like a compressive member, and it will remain straight and in stable equilibrium. Certainly it's going to have stresses on it, but the stresses are going to be easily quantified. If it exceeds that amount, that of course is going to cause the column to become unstable, and specifically it's going to cause the column to buckle and fail. When studying an ideal column, we need to understand the column's behavior. As I mentioned, as long as the load is below the critical load, the column will remain straight. On the other hand, when we hit that critical load, what we find is this first equation has been met. This is a measure of the column's stiffness. It depends upon the modulus of elasticity, meaning the stiffness of the material, and the overall shape of the column. And this gives us an idea of how fast the rate of change is going to be in terms of the deflection. This is going to be equal to the moment. The moment's going to be caused by this applied load P, and V, which is our deflection, meaning how far out of straight has it become. At that critical point, we are still in equilibrium until suddenly something's going to potentially change. We can reorganize this equation, potentially solve for it, and if we go through, we have a double integral here, right? This is, of course, the displacement and the rate of displacement and the rate of displacement, so essentially the acceleration. And this is going to depend upon our force, our modulus of elasticity, our moment of inertia, and the initial displacement magnitude. If we go through and integrate it, we can determine a general solution to this problem. Our general solution is that we have a constant times sine times this quantity here times x. Again, another constant times cosine, again, this general quantity here times x. Problem is we need to know what these constants are. So to solve this equation, we take a look at our boundary conditions. At x is equal to 0, we know we have no displacement. This is one of the n's. As a result, when we plug that in, we can show that C2 has to be equal to 0. So we're only left with this C1 term. Can also know that the displacement at x is equal to L is going to be 0. right? There's going to be no displacement at the other end. So we can show that C1 times sine times the square root of P divided by EI with the x equals L quantity is going to be equal to 0. If that's the case, since we know this is equal to 0, we can just remove C1. It can be divided out. And we know to satisfy this equation, the sine is going to be equal to 0 at any time that n times pi. So 0 case, n is equal to 1, n is equal to 2, n is equal to 3. All of those will give us the sine of that value is equal to 0. Now, to get that, we know that our p must be equal to then n squared pi squared times ei divided by l squared, where n is equal to 1, 2, 3. Now, the first of these we run into is for n is equal to 1. This is going to be the smallest value of p. Right? At that point, that's what our equilibrium analysis is going to give us for our critical load. And this critical load, this is essentially the minimum load that's going to cause buckling, P sub c is going to be equal to that value we just solved for, pi squared times EI divided by L squared. This is the Euler column formula, and this gives us a number for any column that has pin supports at both ends. So you may be asking yourself, what happens when n is greater than 1? Well, n greater than 1 predicts additional failure modes. So for example, if we take a look over here, this is a potential failure mode that the column fails in an S shape. But for this type of failure to occur, the load would have to be 4 times the critical load. And in fact, this will never happen because at the critical load, the column is going to have already failed, so it would never be able to support that load going forward. You'll often see this Euler column formula expressed using a term known as the radius of gyration. The radius of gyration is defined as the square root of the moment of inertia for a column divided by its cross-sectional area. It could also be written as the moment of inertia is equal to the area times the radius of gyration squared. This particular property has been developed to simplify calculations to a certain extent. And keep in mind, it's a constant for a given column. The fact is, you will find this particular property shown in many of the tables, for example, structural steel shapes or dimensional lumber. And keep in mind, what we're going to be looking for is the minimum moment of inertia, because it, of course, would fail in the least stiff way. So the minimum moment of inertia shows the area where the column is going to bend the easiest. If we put that into our Euler formula, we'll find that our critical load is equal to pi squared times moment of inertia times area times r squared divided by KL squared. You're saying, well, that really didn't make it any more simplify it. Well, let's take a look at a few additional pieces of information. One, we're rarely looking for the critical load. Oftentimes we're looking for the critical stress. So our sigma sub c would be equal to pi squared E divided by this KL over R. Keep in mind that KL over R term is an important term. And again, it's a constant for our particular column. So it's something that we can use again in our calculation or in our tables. Now our critical stress, sigma c, this is going to be the average value of the stress. Right? This is going to be the cross-sectional area, and of course it's going to be the critical load divided by that cross-sectional area. In terms of that KL, that's what's referred to as the effective length of the column. We'll discuss that further in the next section. In terms of the buckling that we're trying to work against, as I mentioned, it's going to take place about the axis of the minimum moment of inertia. Again, that's the particular alignment where the column is the least stiff. This is going to be equivalent to a minimum radius of gyration, because keep in mind radius of gyration depends upon moment of inertia. So what we're there mostly often going to be looking for is the minimum radius of gyration r. That's what's going to determine our critical stress and our critical load. So this ratio between the effective length KL and that minimum radius of gyration R is referred to as the slenderness ratio. And we're going to use that widely in our column design process. This chart shows the relationship between our slenderness ratio and our critical stress, sigma C. Slenderness ratio shown on the x-axis. Critical stress is shown on the y-axis, and we have a series of contour lines based on different materials, with wood being at the bottom, with a relatively low modulus of elasticity, magnesium a somewhat stronger material, aluminum stronger than that, higher level of modulus elasticity, steel being the highest one we normally see. Essentially what this is showing is it's showing this particular relationship here in a graphical representation. Yes, keep in mind, since you're seeing the modulus shown here pretty regularly, you should realize that the Euler formula does depend on Hooke's law. So it's essential that any stresses that we look at have to be below that proportional limit, right? It has to be in the elastic region. And this entire formula will not work if you exceed that. At least it will not give you incorrect values. Now, that's rarely a problem with columns because due to their inherent stability, we oftentimes won't see stresses come near that proportional limit, but it is something you want to make sure you guard against. So if you recall, we started this conversation by asking what makes something a long column? Well, it has to do with this relationship between critical stress and proportional limit. As long as the critical stress is less than the proportional limit, then this needs to be treated as a column and analyzed using the techniques that we're discussing. On the other hand, if the critical stress is higher than the proportional limit, then of course the column would fail just solely in compression, and this type of analysis is unnecessary.